fields like combinatorics, topology, and algebra with the developing structures, discrete structures, which are appearing from the problems appearing in pure and applied mathematics, and as well from the other sciences like computer science, engineering, and biology. And today's topic is uh, phylogenetics and polytopes. So over to you, Dr. Delucchi.
Thank you very much. Uh, I'm really happy about this invitation. It's happy to see the old friends and yeah, uh, and thank you for having me here. Um, as as uh, 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 as was said, you know, please don't hesitate to ask any questions in the chat. So I have taken that this is, well, a spirited seminar series and with a kind of a wide audience. And so although I can really not claim to be an expert of all of what this introduction was talking to, I like to, you know, take inputs from different fields. And so what I will try to do is to give kind of a general overview talk. I'll try to be as non-technic as possible, try to show some picture and try to suggest some problems that perhaps you can think about, okay? And again, really please feel free to ask question, to interject and so on. So let me start by, well, talking about what is the connection with phylogenetics, right? So here is the first picture. That's a famous picture. It's from the middle of 19th century. It is the so-called tree of life, right? As Darwinian evolution theories were taking foot. This was the first attempt to actually write down, to draw a tree where all the known species are organized according to what is the common ancestor, right? So this, here we have two species and the common ancestor down there. Now, of course, back in the time, the relationships between the species were mostly about maybe appearances, for example, right? I don't know, some birds have the same shape of the beak, or you have some physical features in common or not in common. Nowadays, computational phylogenetics is based on genomic analysis, basically. And if I can try to give a very quick and rough introduction for the purpose of this talk, I'd like to maybe summarize in this picture that I have in front of you and in front of me. So the goal of computational phylogenetics is to infer, to extract evolutionary pattern on a basis of, we look at genes, right? And it goes like this. So you have maybe a set of species that you want to study and know who has evolved from who, right? And now you look at DNA sequencing of these genes. Right? Now, you look at a special gene, you choose your preferred gene, and you look at how this gene appears across all the species. Now, I am told that biologists have ways to say, well, you know, these two appearances of the same gene, they are similar or not so similar, and you can quantify the dissimilarity, right? So let's say we choose one gene and we look at different appearances of these genes across different species, and biologists can give us a measure of dissimilarity among these genes, right? What's a way for us to represent this dissimilarity? Well, we can think maybe the different appearances of our gene are some black dots, right? and the measure of this similarity we can understand as a distance function, right? These two guys are more similar than these two, right? So what we do have in mathematical terms, we would say, well, we have a metric space, right? We have a set of, in this case, of, let's say, occurrences of a gene across species. And then we have the genetic dissimilarity, that's the distance. And the Darwinian paradigm tells us, well, what we should get is a tree, right? Is some kind of metric space that can be represented by a tree, where you see here somehow it is usual to put the root of the tree on the bottom and the leaves of the tree in the root at the top and the leaves at the bottom, right? So you may understand that these are the species that we kind of see today, maybe the last steps of the evolution, and then these two guys have this common ancestor. Now this metric space tells us a little bit more than just this guy is the common ancestor. It tells us, you know, how far back the mutation goes, right? What can happen, right? If we have our set of, in this case, let's say 6 species, right? We organize them according to the distance given by a fixed gene. In order to write this as a tree, we may have to introduce new vertices of the tree. Here is a dot that I have colored white to say, well, it's not one of the DNA sequences I have really in front of me in my database, but I have to postulate that there will have existed, you know, I don't know, this something that I don't observe today, but perhaps this is a species or some kind of mutation that happened at some point. Okay. I hope this is okay. That's our first step, this arrow, right? I have, from some biologists come to me with you know, a set of species, and for every gene a measure of dissimilarity. Our Darwinian paradigm tells us this set of input data is really a set of metric trees. Okay. Now the second step is, now I have a lot of trees, one tree for every gene, right? There are more than one gene in one species. So for every gene, I have a tree, the so-called gene tree. And I have to somehow aggregate these several trees into one output tree. I want, as an output, one tree for this species. And I want to look at all my input trees in the space of all trees, and there I want to aggregate my data, right? I have lots of elements in the space of trees. I have to get one single output tree. Okay, so that's my quick and dirty introduction to you know, 2 basic steps of computational phylogenetics. Okay. How do I find the distance? That's a very good question. Well, if I just put it like this in this picture, then, well, I didn't tell you how long these edges are, right? So you could say the edges are length 1, and if every edge is length 1, then you can count steps, right? But you could give some weight to every edge, right? You could say, we could say that this edge is length 3, this edge is length 1, this edge is length, I don't know, 2, and then you add the length, and from here, from a point to another point, you look at the shortest path, right? And that's the distance. Of course, in a tree, there is a unique path, but in general, that's what you do. Did I answer the question of, okay, you are welcome. Good.
May I ask a question?
Yes.
Okay. You are here this space X, but you have another element which is denoted as white dot, right?
There is, yeah, exactly. I mean, I was a little bit stuck. So what I mean here, the X is the set of all the black dots.
Yes, yes. You said that this is just the black dots. Then how you incorporate with this white dot? I mean, this is something different space.
So, right, I will come to speak about this later, more precisely. But the thing is that my space is the black dots, and I have defined some distance. And there are canonical algorithms that they say, well, if this is a tree-like space, then it has a representation with a graph. This representation is unique, and you might have to add points, right? This is a vertex of the graph that is not an element of my metric space.
Okay, okay.
I will, in a couple of slides, I will explain this more precisely. Okay, but for the moment, the black dots are your species, and in order to fit them on a graph, you might have to add, to use some vertices of the graph that are not really elements of your, do not correspond to elements of the metric space. Okay. Good. This is just the first, very informal introduction, because I want to tell you the two kinds of questions I want to address. Okay. If there are no more questions, please let me know. So here are my two questions. So first question. It turns out that the kind of measurements that biologists do, the data that we have are not naturally in this tree form. Okay, the metric spaces that we have are not naturally trees. Okay? For different reasons, biologists would like to be able to do the same game here, to do the same kind of reasoning, but not only with trees, with slightly more general metric spaces. For example, some that one might represent like this. So this is a graph. If you think that this is a metric space on 4 elements, and you take, let's say, every edge length 1, okay, then this metric space you cannot represent with a graph that is a tree. And that's a slightly more special kind of metric space, which is called a split metric. It is not important at this moment to understand the definition of a split metric. If you already have encountered it, then this will refresh your memory. If you did not encounter this split metrics, let's not go into detail right now. So the first question is, can I do this game with metric spaces that are not trees? And for metric spaces that are not trees, we need to, it's not practical to look at this graph, right? I'll explain later. So this is the question I will address later on. But first, I want to address the second question. Let me explain it. You see here, right? Remember the story. I have many trees that stay with trees, right? I have many trees, and I want to have a single output tree. In however way I want to do it, I need to have an algorithm for this. Okay, for a rule that given several trees gives me one tree back. Usually it's some kind of a statistical process in the space of all trees. But recently there are ways, algorithmic ways to study this, very generally this problem of data aggregation. And the question is the following. If more species are sequenced, I know more and more data, right? Maybe first I know only 1,000 genes, and so I have 1,000 trees to do the computation. Now somebody comes and gives me 500 more trees. Now the question is, can I have a system where I take my old tree and update it with the new data, or do I have to go back and do the computation from the start? Okay. So these kind of questions are handled by consensus theory. Okay, I'm now going to another slide to try to explain what is consensus theory. So our overarching situation here, we want to go from measure of genetic similarity to a single output phylogenetic tree, right? We first model this dissimilarity as a metric space that we'll address later. And secondly, I have several metric spaces, in this case, several trees I want to aggregate. And the abstract study of aggregation algorithms is consensus theory. Okay, the references here are classical Bellera, Holmes, Fogman, and this McMorris and Barthélemy is a book about consensus theory. But what is consensus theory? Okay, in general, this is just a study of data aggregation algorithms. Here I have several colored circles. I have inputs of the same kind. They are all disks, right? But with different properties, different colors. And somehow I want to decide one single color as an output. Now this depends on the situation. And depending on the situation, I might have different criteria, or, you know, I want that this data aggregation algorithm does something special for me, depending on what I want to do. Now, the origin of this whole thing that explains also the name, the origin is social choice theory, and that, you know, the pioneering work was by Kenneth Arrow, who had the Nobel Prize in I think economics for this, or political science somehow. So social choice theory, let's say the natural example is elections, right? In elections, there are several inputs. Every voter gives an input, but then you have to have a system to take all the inputs and decide one single outcome, right? Between all of the options, all of the candidates, let's say only one, exactly one gets elected. So usually one of these consensus methods is majority rule, right? You collect all the inputs, the preference of everybody, and the guy who, or the person that has the majority of the preferences gets elected. This is one possible system, is not the only system. Arrow studied the limitations of this system, in fact. But let's not get in too much into this kind of social business. Let's see what happens if we want to aggregate trees. Okay, for us, we want to study consensus among trees. So we have several, let's say, phylogenetic trees. I have now simplified. So let's say I have numbered my species, and the species only appear at the leaves, let's say, to simplify this, right? And now the first gene gives me this tree, the second gene gives me that tree, the third gene gives me that other tree. Okay, and somehow I need to say, okay, then what is the tree of the species, right? What is the outcome of the tree? So what are desirable and reasonable properties for such an algorithm? Okay. First of all, some basic regularity properties. So, of course, if I change the order of the input, the result shouldn't change, right? We expect that. Right? Then if I change the labels of this, if I change the names of the species, so to speak, if I change the labels everywhere, well, I should be able to just change the label of the result and nothing changes. Idempotent means, well, if all my inputs are the same tree, then my algorithm should output this tree. That seems to me reasonable. And these kind of basic, reasonable things, they usually go under the name of regularity. Then there's a second type of desirable and reasonable properties. They go under the name of Pareto properties, and I summarize with shared local features appear in the output. What does it mean? You see, look at 2, 3, 4. I am observing that 2, 3, and 4 basically have the same behavior in all the input trees, right? Because you see 2 branches and then 3 and 4 branch. The same happens here. First 2 branches and then 3 and 4 branch. Then 2 branches first and 3 and 4 branch later. Number 1 is positioned differently, but if I only look at 2, 3, 4, I always see the same kind of tree, this here. Excuse me. So the Pareto property for rooted triples, for example, tells me, well, okay, if I am observing the same kind of rooted triple everywhere, then the output tree should also display this rooted triple. Okay, this is a feature, a little local feature that if it appears everywhere in the input, it should appear also in the output. Okay, that's Pareto. The third and last kind of property is this kind of data scaling that I was mentioning before. One possible way to make this precise is what some people call associative stability. The idea is that I want to be able to just update my results and not redo the computation. So if I now don't have only 3 trees, but I have a 4th one, I want that the whole computation has the same result as my old consensus tree, updated by my new data. Okay, so instead doing the whole computation, you want to be able to take the old computation, the old tree, and update it with the new data. Okay, this is called associative stability, not by me, not by us, but by people who study this for a living and came up with some questions. And the usual question is, well, do regular Pareto and stable algorithms exist? Okay. So, for example, a question of Brian, Francis, and Steele was, does such a method exist that is regular, Pareto on rooted triples, and associatively stable, right? I just explained. So we proved that this is not the case. Such an algorithm does not exist if I allow for trees that are big enough. So if I have more than 5 leaves, these algorithms do not exist. Not even if I kind of relax some conditions. You can look in the paper we have in Systematic Biology in 2020. And, you know, let me, before I say a word about a little bit of mathematics in this context, are there questions about this kind of setup? Of course, I was not very precise, but the idea is that you want algorithms that take trees as an input and give a tree as an output. You want these kind of properties, and in particular, you want Pareto with rooted triples and associatively stable. We prove that such algorithms So they were conjectured to exist. Here we prove that they don't exist. Now, how do we prove this? Well, we prove this in a way that I don't find satisfying. We reduce this to checking a finite number of cases and then check with the computer that this finite number of cases doesn't work. Not satisfactory. The mathematical reformulation that I would like to pose to you as a problem is the question is, yeah, for n smaller or equal to 5, these algorithms exist. They can be described. We have them in our paper. For any tree structure, then we should discuss what is a general tree structure. This is, I think, these results specifically is for what they call phylogenetic trees. I did not give a precise definition. You can see it in the paper. I think these are, first of all, yeah, I would refer to you to the paper or to the questions afterwards. But yeah, they exist for every phylogenetic tree, yeah, without other conditions than this. Okay. Now, how do we see it mathematically? Well, a commutative, idempotent, and associative operation on a finite set is defines a mid-semilattice. So it defines a partial order that is as the property of being a mid-semilattice. Now, this action of the symmetric group gives us a group action on a semilattice, and this Pareto property you could model by saying, well, on my semilattice I have a certain function towards a target semilattice. Now the question becomes, I have a semilattice given the rooted triples, I have a set with a map and an action of the symmetric group, and the question is, does it exist a semilattic structure on my original poset that makes this map equivariant and satisfies some order relation, order theoretical properties, okay? We describe this in the paper. If you want to, it's a short description, please go and look at it. And this kind of problem, I have a set, I have somehow a map to a certain semilattice and group actions, and I want to know whether there exists a semilattice structure or not. I have never heard before. So if anybody has experience with this, please let me know.
So can I have a question?
Yes, please.
Okay, so the group you mentioned here is this the automorphism group of this tree you're talking about?
It's the we can have any tree on the input side, right? The group is, the action is really switching the names, right? Here is the symmetric group on 4 elements, for example.
Okay.
Right.
So usually we call it the automorphism group of the tree. Perhaps maybe you are talking about that, and then you have the action of this group. So how you define the action? So please explain. I want to know about this. So
the action is, so for example, let me yeah, so let me act with the transposition 2, 3, right?
Mm-hmm.
And it will give me this tree.
Okay, so the group in this case will be S4 you are talking about, this symmetric group of 4 elements.
Yes.
Okay. Okay. So, but if you have trees with different
Right.
let's labels.
This is yes. So let me try to sketch here. So what we have is the set of trees with n leaves.
Okay, so n will be fixed for all the trees.
N is the somehow the number of species we have in front of us. It's fixed. Right?
Okay.
And you have an action of, let's say, Sn.
Mm-hmm.
And then yeah, then you have some map to some semi-lattice.
Okay.
That also has an Sn action.
Mm-hmm.
So F is given. So F is given, this is given, the actions are given. And then the question is, does it exist a semi-lattice structure? Does it exist a partial order on this that makes my, so that this is equivariant and some lattice theoretic property is satisfied? That's the question.
Okay.
Thank you for your question. I hope I answered. We can talk more precisely later, but I hope I have given at least an idea.
Mm-hmm. Okay, thank you.
Yes. And again, let me refer you to the I can send you the paper. It's also on the archive, I think. There it is formulated precisely. Thank you for your interest. Okay, so that was what I wanted to say about this consensus business, because I thought it's, it's kind of not intuitive, but kind of direct relationship between an algorithmic question and kind of a strange but interesting combinatorial questions that I don't know how to really treat. Okay. And in general, the program would be, well, if you do this consensus theory, you have books with pages like this, right? Every special property will be studied. Is it possible? Does it exist an algorithm? Does it not exist an algorithm? But I don't know of any systematic theory. And so this way to treat mathematically, for example, these maps of semi-lattices, what's the reason why they exist or not? Well, this would give us a characterization of abstraction and does maybe a prediction, right? So algorithms like this regular Pareto stable do not exist, but maybe, since if I know the abstraction, I can at least say, well, maybe I can modify the properties and I can find some algorithm with that other property. Okay? So that's the program. But at the moment, let me go back. So we talked about consensus stability. And now I want to say a word about maybe this kind of strange other question, right? I want to deal not only with trees, but with more general metric spaces. For this, and to answer the question of Dr. Shaheen Nazir before, let me, at this point, I'm getting maybe a little bit more precise. I think this may be welcomed by some of you. And say, what do I mean when I draw these pictures of graphs with points, black and white, and so on? Okay. I want to talk about metric spaces. A metric space is a symmetric non-negative function that satisfies the triangle inequality, right? And is zero only if the arguments coincide. One way to represent such a metric space is via a graph, right? We have a simple graph with a weighting. That was the question of Dr. Tokir Shah. So I usually have a graph with weights, right? And the distance of two vertices is the weight of the lightest path that joins X and Y. And this is a metric on any subset of the vertices. Here I have chosen a 3-element subset of my vertices. So on this set ZVW, I have a metric given by this graph, right? The distance of V and W is 3, because V and W, the shortest path is this, okay? The distance of Z and W is 3. There is only one path. The distance of Z and V is 6, because the shortest path is this, right? D is a metric on these 3 elements. So that's what I think when I see these graphs with white and black dots, right? I have a graph with weights, and then the black dots are going to be the elements of my metric space. I hope this answers the question before. And then I call a metric a tree-like metric whenever I can write it like this, where the graph G is a tree, by which I now mean any graph that is connected and does not have any cycles. Okay. Now, when I can represent it as a tree, then this tree is in some sense unique.
May I ask one question here?
Yes.
Okay, here you have chosen X to be a subset of a vertices set, right? Here X can be chosen any set from the vertices, or you just need to pick like a tree which
no. I can choose any set of vertices. I could, for example, the example 2 is I pick this guy as well. Let's say this I call, I don't know, Y, okay?
Okay.
And then I would have, I don't know, maybe then the same is true, and then dyv is equal to 2, dyz is equal to 4, and so on. And this is a metric on y.
Okay.
That's
okay.
Any graph with weights and any choice of vertices gives me a metric via this weight of lightest path. Okay.
Good.
That will be actually important later. Thank you for your question. So
one more thing.
yes.
Should we need to pick X with some special cardinality, or any
So for me, let's say finite.
Okay.
Okay. Now the question is that you can have different graphs, different weighted graphs representing the same metric. Okay. And so the graph is not unique, not uniquely determined by D. Okay. This is only true for trees. Okay. So this is work by Bandelt and Dress in the 90s. Right? If you have a tree-like metric, then, and you only know the metric, there's a canonical way to reconstruct the tree, right? And everything works wonderfully. In general, the graph is not uniquely determined by the metric. So the thing is, the graph can tell us the metric, but it's probably not a very good combinatorial invariant of the metric because it's not unique. Okay. Now, what I want to do today, so the polytope I was talking about in the title is a suggestion of what should be an interesting combinatorial invariant of a metric space. Let me go directly to that. So let's stay with our finite metric space. Now, tree, not tree, I don't care. It's just an abstract finite metric space. And in the Euclidean space that has one coordinate for every element of my metric space, I look at these kinds of vectors, right? That's the E, I, Ej are the standard basis vectors. And I will say standard basis vector I minus standard basis vector J divided by the distance. The convex hull of this guy is called the Kantorovich-Rubinstein polytope of this metric space. Let's do an example. Here's an example. A metric space on 3 elements, and all the distances are equal to 1. Okay? Then I am in R3 because I have 3 elements, right? And these vectors are, every possible combination of 1, -1, 0, and the distance is 1. Okay, so in this case, the set of vectors is the set of roots for a Cox-Successor system of type AN, and the convex hull is this, right? So this lives in R3. I'm cutting it with the plane sum of coordinates equal to 0. Okay, that's a polytope that you can associate to every finite metric space. Let me see, if I change my metric space, this is a new metric space. Now V and W have distance 2. So when I have V and W here, I will have to divide by 2. In fact, you remember here there was a long vector before, and now it's divided by 2. The convex hull now is not an hexagon anymore, it's a rectangle. So the metric space changed, my polytope changed. Okay? So the name of the game here is, can you tell me, I give you a metric space, can you tell me how the polytope looks like? This is difficult and open. Okay? Depending where you come from in mathematics, you may be more familiar or you may like this other description. I want to call, so not I, but the Lipschitz polytope is the set of all points that represent Lipschitz functions with constant 1 on the given metric space. This is another convex polytope, and it turns out to be dual to the original guy. So without going into this, so this combinatorial duality, I'm talking here about polar duality, in fact. And polar duality is actually combinatorial equivalence, right? So if I'm interested in things like faces, number of faces, and so on, the dual is as informative as the original one. And so that's why I call both of these, to refer to both, I refer to fundamental polytopes of metric spaces, right? The question that was asked by Vershik in 2010 was, well, can you classify metric spaces according to combinatorial properties of their fundamental polytopes? Okay. So what do I mean by classify metric spaces? Well, let's go back and say, well, if I want to look at the graphs, right, at the space of metric spaces according to the shape of the graph. So for the 3-element set, for the 3-element metric spaces, you see, to specify a metric on 3 elements, I need to specify the distances, right? And then since it's symmetric, I only need to specify 3 distances. None of these should be 0, so the space of my metric spaces will not contain the coordinate planes. Okay, so you see this is not contained. When it touches the planes, it's not contained. And otherwise, I have my triangle inequality, right? I have this kind of triangle inequality. And this cuts a cone. In this case, it's a triangular cone. And here I have represented a slice of this cone. And every point in this cone represents a metric on 3 elements. And so in the very barycenter, I have the tree with all 3 legs same length. In this race, I have these kinds of yes. So yeah, that's a very, very, very good question by Mr. or Mrs. Tukir-Shah. How about the converse? We know the polytope. Can we find all the metric spaces? Sorry, Mr. Associated with it. Do we know if there is a one-to-one relationship between metric spaces and polytopes? Ah, how long can I stay? So open, and in particular, but I can answer the last one. It is absolutely clear, it is clear that different metric spaces will have the same combinatorial type of polytope. Okay, so let's look to end your question. To end answer your question, let's look at this picture I have on right now. In this picture, I am looking at the metric space and I'm looking at the graph as a combinatorial invariant. Okay. The nice thing for 3-point metric spaces is that every metric space is a tree. Okay, so all the graphs here are trees. Now, if I fix a special metric tree, exactly one, then of course every metric space corresponds to exactly one special metric tree in this case, right? But I can say, well, okay, all the graphs that look combinatorially like this, align with V, U, W, they correspond to a face of this cone, right? All the graphs that look like this with 3 legs of equal length are a ray that here is only 1 point, but one needs to think of this as a ray. And so on. All the metric spaces that have such kind of tree where the leg of W is longer than the leg of V that is longer than the leg of U, they fill this kind of cell, right? So what I have is a classification of metric spaces according to these graphs, right? By the way, of course, if you know the graph precisely, you know the space. And if you know the polytope precisely, then you, of course, know the space because the edge, the vertices are giving you the distances, right? But the tricky question is, if you know your polytope is a cube. So what are the metric spaces that have a cube? Okay. What are the metric spaces on 3 elements that have an hexagon as a fundamental polytope? I'm going to tell you right now, okay? So, right? So, turns out that for 3-element spaces, it's always the same cone, right? The metric spaces are always the same set of metric spaces. Now, turns out the 3 faces have rectangles, of course, with different, rectangle with different vertices, right? And everybody in the middle has a hexagon. Maybe a hexagon that is not regular, right? Maybe a little bit squished hexagon, but as far as combinatorial type, this is what it is. Okay? So that's the idea of what I'm thinking about here, right? So I have this definition of polytopes, and the question is classify metric spaces according to the fundamental polytopes. I see now it is 50 minutes from the theoretical beginning, but since I have started 3 or 4 minutes late and there were many questions, I want to ask Dr. Shaheen Nazir whether I can go on maybe 3 or 4 more minutes.
Yes, yes, sure, sure. Why not? You can take.
Yes. Okay, so this is the question. I want to just say why I think this is an interesting topic. Okay, first of all, I didn't invent these polytopes. They come from optimal transportation theory. In fact, some people call this Wasserstein polytopes. For us, they stratify the space of metrics. And remember, the old picture, right, with the trees. So basing on the graph, this is not a good, the graph is not unique if I go beyond trees. But the polytope is unique. It only depends on the metric, right? If you are interested in dynamical systems, and you, for example, look at these Kuramoto type models of oscillators that influence each other, this also, the influence system is a graph, and the intensity of the influence is a weight on the graph. And the number of steady states of such dynamical systems are bounded by the number of integer points inside my polytope. These guys are not only classical polytopes, they are also polytopes in the tropical sense. And they are more general than edge polytopes of graphs. So this is something from commutative algebra, something like symmetric edge polytopes of graphs. They have to do with graph ideals. And these things, they are quite difficult to get to themselves. We wrote a paper with Alessio and Mateusz about it. And we point out our polytopes are even more difficult, okay? Our polytopes are special sections of symmetric edge polytopes of graphs. Right? And people started using these things in algebraic statistics. So this is just to make a little bit of advertising for this kind of question, right? And the picture is this. Remember, the old picture is very heavily subdivided according to the graphs, but here I have a kind of a, I would say, easier stratification, right? And more especially, I can stratify this even for more than 3 elements, even when I don't have a tree, okay? So that polyhedral complex, the stratification, should give me a good model of the space of metric spaces that are not necessarily trees. And the ultimate goal is to use this as a space on which do statistical modeling, as people do nowadays on the space of phylogenetic trees. Okay? We can go to the question later. I want to show the last slide on, I told you these polytopes are difficult. Actually, I would say we do almost nothing. Let me tell you everything that is known as of today about these polytopes. First of all, there are some kind of, asymptotic results, right? A number of different structures, if I fix the size of the metric space and some generic things, this was done by Gordon Petrov and Yevgeny Zhivalyevich. And then, as far as I know, the first structural result is the one we obtained with my grad student, Leonard Oesley. And that's a bummer, it's for tree-like metrics, okay? In this case, if my metric is tree-like, my polytope is a zonotope. It's a Minkowski sum of segments. And if you look at the tree, you can write down an explicit formula for the number of faces, for example. Okay. And how do you do it? I'm sorry I don't have the time, but this is a very lovely story. You look at the tree, you look at the matroid. In fact, you look at an hyperplane arrangement and you write the character. This I am, of course, saying for Dr. Shaheen Nazir of every other people who likes arrangements of hyperplanes. For every tree, there is a special arrangement of hyperplane. You write down the characteristic polynomial and you evaluate the characteristic polynomial and you will get face numbers of these polytopes for the case of tree-like metrics. with some commutative algebra methods, we can also compute phase numbers and integer points in polytopes for a little bit more general things. You know, some phylogenetic networks, but this is still not satisfactory. So we still need you to help us with this. So in conclusion, I am going towards, you know, I kind of don't like this. I like this more, okay? And especially in higher dimension, with more metric spaces, but still it is open, right? So I give you a metric space. Can you tell me, I don't know, the number of faces of the polytope? This is completely open beyond the tree case. And it would be really, really interesting to know something like this. The general picture, I think, you know, we are approaching this now with tropical geometry models, methods, and we think that this kind of fan structure is a sub-fan of the secondary fan of some special point configurations related to root systems, right? But I think my time now is really over, and I want to just leave you with two questions. Do you like to think about groups acting on posets? Then have a look at consensus methods and try to, maybe this is a good problem for you to think about. Otherwise, do you like polytopes? Well, here you can see our paper with Linard. It's on the archive as an entry point, right? This is only part of the story, but then you can get the definitions. And I give you a special kind of metric space, even for a subclass. Can you tell me the number of, I don't know, even the number of vertices? Anyway, I don't want to take too much time. I stop here, and I thank you really for your attention and your questions.
Okay, thank you so much for very nice talk and very informative talk. Okay, I have, is there any question from the participants? You have already answered so many questions, right? I have a few questions, like one or two.
Yes.
Okay. You have associated to KR polytopes, right? Which is, I mean, connected to the metric space. My question is, can we define different polytopes associated to the metric space? Or is this the unique one at this moment, or in the literature? Are there other polytopes which are associated to the metric spaces?
This is this is not an easy question. This is actually I mean, the very short answer is that you can define whatever you want. The question is, what do you want to do with it, right? So, but in the literature, you ask a very good question. So there is a very fundamental and famous work in geometric analysis that goes back to Isbell in the 60s about what he calls tight spans of metric spaces. So, and some people refer to this as the polytope of a metric space. The story goes back to Isbell. It was taken up by Bandelt and Dress in the 90s. I can give you references. This is a canonical, you know, really a canonical construction in geometric analysis. It's called, right, the tight span of the metric space, but this is not a convex polytope. We would call this a polyhedral complex. Okay, it is so for tree spaces. For trees, this is exactly the tree, the metric tree that you are looking at. For non-tree spaces, this is usually built out of segments, squares and cubes, and so on. That is something that exists. That is something that has been studied a lot, but from a combinatorial point of view, it is very complicated and somehow not natural. It is very natural from a analysis, geometric analysis point of view, from a categorical point of view, not so natural for us. And especially, it gives us weird stratifications. It's difficult to, sorry, right? This should be for me a model of, if you go you see Isbell and this tight spans or injective halves, right? But if you subdivide your set of metric spaces according to this, you will have a very fine, a very detailed description, but is accordingly difficult to manage. Mm-hmm. So the reason I like these polytopes is that I kind of like this picture better. So I don't know if I've answered your question, but yes, absolutely. You should know there is this famous work about injective halves and tight spans, and actually an open question that I have a hunch, but I'm not sure. I don't want to say it now that I am being recorded. But the question is, take a metric space, or two metric spaces. They have different tight spans. Do they have also different polytopes? Or maybe they can have same tight span but different polytope. They can have different polytope but same tight span. This is at this moment, let's say, not fully clear. I don't know if I answered. It is probably more confusing than.
Yeah. Yeah, sort of. It answers my questions as well. Okay, so this means because this is the problem which you mentioned, that they classify the metric spaces. Who tells us about the combinatorics of these polytopes? So I would just want to know that can you give me some references, or can you tell me some literature?
Absolutely.
Which kind of metric spaces has already classified? I mean, like
only trees. So the question. So the source is this paper of Vershik in 2010, and I mean, not because I want to make advertisement, but I would say, if you look my paper with Linard, there we have the references. Okay. So then you can find exactly which paper of Vershik I'm talking about, and also you can see the state of the art today is really not different than here. Okay. So maybe the only advancement is here. Yeah. And here, there is a recent paper by Sturmfeld, Venturello, and so on. It really tells you that it is interesting for algebraic statistics, but doesn't give really a new, or doesn't answer the question. And here is just the context in the concept of tropical geometry. But yeah, I honestly I don't want to sound, but maybe the paper by Vershik in 2010 is interesting. Maybe you can look at, so this is shorter than the other one, and probably gives you a couple of references that are interesting to try and start and look. And you can always email me. We can discuss this further if you have any.
Sure. Okay, one more thing. You mentioned this, the last paper in 2019. You said that you have talked about some different polytopes.
We can now do polytopes for graphs that are of this kind. So first of all, we only can do if every vertex is black.
Okay.
In this paper, okay, in this paper, only all vertices black, and here any kind.
Any kind.
And here we can do anything where the graph is planar and it is either an odd cycle, or you glue even cycles by an edge, or you glue even and odd cycles by a vertex. If I'm not, so it is very strange. It is very ad hoc. And
Okay.
Can you get my email? Of course, you can get my email.
Yes, 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 yes.
Yes. Yeah. Let me give you my work.
Okay, is there any other question or comments? From the participants? No question. Okay.
And if anybody has access, has difficulty to access references, I can provide PDFs. Just email me.
Okay, okay. We will try if they are on archive, then otherwise we will write you. Okay, so there is no question. So let's thank the speaker again. Thank you so much for this wonderful talk.